get started. Incidentally, I put a note on the board for Jacqueline and Natalie. Would you folks see me just for a moment right after the class? Today I want to talk to you a little bit about nerve cells and neuroglia. These, of course, are the building blocks of the nervous system. I know that most of you have some acquaintance, and some of you have quite a very close acquaintance with these elements. So I'm not going to belabor the point, but for those of you who perhaps haven't had as much contact with some form of neuro until now, it seems wise to talk just for a few minutes about neurons and neuroglia. Now, the neuron is, of course, the basic communicated unit of the nervous system. We know that nature goes to great trouble to manufacture an excess of these. Some people have suggested that nature, for the human, may manufacture as many as 300 or 400 billion nerve cells, and then slough off many of these so that we think we end up with about 100 billion. You've all heard that number. Nobody's ever counted it. I feel uncomfortable retailing it to you because I haven't counted them myself. 14, but not 100 billion. Now, the neuron, as you know, is an element sheathed in a phospholipid membrane, and in the membrane float an enormous number of small multi-molecular structures, things like receptors and ion channels and transporters and all kinds of exciting things that end up by making this membrane not totally permeable, but semi-permeable, so that there is continuous two-way commerce across the membrane. This, again, I realize that you know, and we're not going to spend time with it simply because it's outside of our own purview. Suffice it to say, the neuron is, in every sense, a living, breathing element, and it is constantly in an interactive pattern with the, what we call the pericellular milieu, the space outside of it. We're going to concern ourselves more with the kinds of neurons and how they develop. Now, in the invertebrate, probably the most frequent neuron is a neuron which we say is unipolar. What does it look like? It looks like that with a single pole, and we call it unipolar. The single pole is the axon, and this, of course, carries information away from the cell which is here. Now, as you look at this, you think, well, I know there are dendrites on those cells. How does this cell get its informational input? The input in the more primitive invertebrates usually was applied or attached to this part here. And the input very often wound itself around this way. Don't worry what it's called. It's just a receptive area at the junction between soma, which means cell body, and axon, which is, of course, the projective component. This was the input. Now, are there unipolar cells in the vertebrate nervous system, which is our concern? And the answer is probably not unipolar cells, but there are very special kinds of bipolar cells which come to look like unipolar cells. Now, first of all, what is a bipolar cell? Well, just like what it sounds, a bipolar cell is a cell that has two poles with two elements going away from it. Now, I told you that we're going to see what we call a pseudo-unipolar cell quite frequently in the central nervous system. And let me show you what that looks like. those are found primarily in the peripheral nervous system, in those structures that we've already mentioned to you. The structures, of course, are the dorsal root ganglia, and they provide the sensory input to the spinal cord and the brain stem. And here's how they develop. A cell first develops as a well-meaning little bipolar cell. And then rather interesting things happen. The two projections begin to move around so that they're getting closer, and you can sort of see what's going to happen in a moment. And finally, they come close enough to fuse, like so. And we have what looks for all the world like one of the old unipolar cells in the invertebrate. Now, why does this happen here and nowhere else? We think it happens, let me take this out now, they're completely fused. We think it happens because this peripheral process that's going out, say, to the skin, is bringing information. And it's going to continue to carry that information this way through the central process, which is going to go, in this case, through the spinal cord. Things are slowed down if information has to go this way, over the broader areal extent of the soma. But if information can go directly up the axon, short-circuiting the soma, the speed of the trajectory is obviously increased. And that, we think, is why you have this curious transition from a typical primitive bipolar cell to a pseudo-unipolar cell. So we've mentioned unipolar, pseudo-unipolar, and bipolar. And then the only place you can go from there is multipolar. And of course, a multipolar cell, just as you'd expect, has a number of projections, mainly dendritic, of course, and usually one axon. One of you asked me, I guess last week, are there any cells in the central nervous system that have more than one axon? So far as we know, not. There is one possible exception, but that's only inferential, so I'm not going to worry you about it. So the most frequent type of cell that we're going to see is a multipolar neuron with a number of dendritic stalks coming out and a single axon. Now, having said that, let me begin to show you the multiplicity of neurons. They are very beautiful. What do we have? Well, we have nothing unless I have my pointer with me, which I should have. Yeah. These are pictures, again, from the great master draftsman of the nervous system, Cahal. Here is a cell, quite simple. It has a small cluster of dendrites at one end and a single axon at the other. Here is, you might say, the antithesis, a rather complex cell. This cell, by the way, that we're looking at here is probably the most frequent cell in the entire vertebrate nervous system. This is the famous pyramidal cell of the cerebral cortex. You'll get to know these very, very well. Notice that it has a roughly pyramidal-shaped cell body. It has a great stalk and apical dendrite, in other words, a dendrite coming out of the apex of the pyramid, and that extends up toward the surface, or actually to the pedal surface. It has collateral side branches along the way up, and then From the base of the cell, you have a number of basilar dendritic branches. And then here, this much lighter line here, this is the axon. And you see a number of collaterals coming from the axon. These cells, as we're going to see, are somehow related to the high cognitive levels of activity that a cortex is able to generate. We do not see these in brain stem. We do not see these even in thalamus, certainly not in spinal cord. So this is a typical, complex, multipolar cell. Compare that with this, which is a typical thalamic cell. Notice that you have essentially, it's a multipolar cell, you have essentially dendritic systems which branch very, very densely, rather closely to the cell. So a cell like this is going to be open to inputs that come rather close to it. Obviously, if the input stops there and the dendrites stop here, there's no communication. Whereas this pyramidal cell is infinitely curious. It wants to know what's happening at every cortical layer. It's a real busybody. And think of all the pileup of presynaptic inputs along that shaft. Think of all the computation that may occur along that. Here's a very beautiful cell. This is the typical Purkinje cell of the cerebellum. You're going to get very used to that too. Not only does this have one of the most remarkable and highly organized dendritic plexuses or trees, the entire nerve system, it has another curious property. We're looking at it head on. If I turn this cell 90 degrees, we would just see a very thin edge. In other words, here you have an example of a two-dimensional, not a three-dimensional, but a two-dimensional dendritic system. Again, this obviously has some very real and powerful physiological fallout. Here is a cell, again from the cerebellum. Here's the dendritic system. And notice that you can see the full extent of the axon. That's the full extent of the axon. What does that mean? This is a cell whose axon stays fairly close to the cell body of origin. Whereas a cell like the pyramidal cell, its axon, remember, starting up here, its axon may go all the way down the spinal cord, maybe to the lumbosacral area. So just think, a 7-foot 6-inch basketball player, some of his pyramidal cells have to support an axon that may be 3.5, 4 feet long. Isn't that incredible? So these are things that we're going to begin to recognize in the multiplicity of neurons. The cells that I've just been showing you, we saw cell body, we saw dendrites, we saw axons. All of those images were harvested through the use of that famous old stain that we've already talked about a lot now, the Golgi stain. And the story about Camillo Golgi, the great Italian neurohistologist from Pavia, is an interesting one. Some of you know the story. Golgi actually was a psychiatrist, and he was working in a hospital for the criminally insane, but he loved the nervous system. And he was trying to get better stains than the old stains were. And the story is, and I don't know if it's true or not, that one night after he went home, the cleanup lady threw some tissue that he'd been soaking in chromate solution. She threw it into, I guess, a spittoon or something, and there was some silver solution in that. He came back the next morning, for some reason, tried to rescue the lump of tissue, and all of a sudden he discovered the Golgi stain. Because the previous exposure to chromates, followed by exposure to silver, produced somehow a very fine precipitate of silver, not just on the cell, but also in the cell, and produced the appearance we saw. So the Golgi stain, as I say, has tremendous historical significance, and it's still used very often in CNS research. The other great family of stains that was so important in introducing us to the structure of the nervous system were the so-called Nissl stains. Now, how do you spell Nissl? It's named after its founder, Franz Nissl. And the family is unfortunate because they early lost an E out of their name. So Nissl is spelled N-I-S-S-L. Sort of anti-intuitive. I guess you should either be a good histologist or decide never to lose an E from your name. Anyway, the Nissl family of stains is built around the capacity of aniline dyes, which are basic dyes, to tie specifically to acidic molecules. And since you and I know that molecules like DNA and RNA are acids, right? These aniline stains turned out to be specific in their capacity to bind to these acidic components. And this is the kind of picture that you get. This is the cell body, stained faintly pink. But the interesting thing is these large purple-blue masses within the cytoplasm. Nissl discovered those, and they were called for years and years Nissl bodies. And we knew they were characteristic of neurons, although we could often see smaller versions of these in non-neuronal tissue. We know now, thanks to the electron microscope, exactly what these are. We'll talk about them in a moment. But then just have in your mind then the fact that in a sense, modern fine structure was built up historically on the backs of the Golgi family of stains and the Nissl aniline type stains. Now here is a single pyramidal cell from the cortex, higher power of course. Here's your cell body. Here's the beginning of the apical shaft. Here are the side branches. And by the way, you can begin to see dendritic spines, not quite in focus. You can see them here on some of the basilar dendrites. When you compare a dendrite with an axon, notice how smooth the axon is compared to the sort of lumpy, bumpy dendrites. This, of course, is the great efferent carrier for the cell body. I've been showing you cells that have rather long axons that may go 3-4 feet in some cases. Here is another one of those cells whose axon breaks up almost immediately. And we call that, strangely enough, a short axon cell. These were also discovered early on by Camillo Golgi, and for obvious reasons, the long axon cell and the short axon cell, both of which he first described, are called the Golgi 1 cell, meaning long axon, and the Golgi type 2 cell, or short axon. Now, the important question is, how short does an axon have to be a short axon? Nobody knows this, but just, I'm going to share it with you folks and keep it quiet. The secret is that a Golgi 2 axon can be fairly long, but the thing that distinguishes it is a Golgi 2 axon never gets out into the white matter. It remains in the gray matter. In other words, it remains in a nerve cell environment. Whereas a Golgi 1 cell, its axon does get out into white matter, and then they go varying distances. So as I say, it's a well-kept secret, don't let it out. But at least that is the right definition of Golgi 1 versus Golgi 2. This just slightly out of focus, but that's all right. Just to show you what a Golgi stain looks like. This luminous yellow or orange background is quite characteristic. Here we see a few cells, incompletely stained, but we see some of them. And it also answers a question that some of you were asking in the review last Thursday, and that is, does the Golgi stain all the cells that are there? It's a very funny, cranky, prima donna kind of stain. After 125 years, nobody yet knows exactly why it works. One of its characteristics is it only stains 1 or 2 or 3% of the cells in any area. That's great, because if it stained everything, you'd just see a black sea. You couldn't identify anything. Today, we have ways, as you know, of very elegantly injecting individual cells with vital dyes or other things so that we can pick up in the greatest possible detail all the dendrites and axonal ramifications of a single cell. While the Golgi is a little cruder than that, its positive is that it stains an array of cells, whereas, obviously, the only stain we get when we microinject is that one cell that we microinject. This is just, again, to show you sort of a panoply of various kinds of stains. Here, obviously, is a Golgi type stain, right, with all the dendrites and so forth. Here's, at high power, a classic Nissl type stain with the cell body, the nucleolus, very, very RNA and to some extent DNA rich, and of course the Nissl bodies, which we wondered about for, about 75 years. And then with the coming of the electron microscope, we discovered that the Nissl bodies were actually what we today call endoplasmic reticulum. Endoplasmic reticulum is a very complex three-dimensional maze, you might say, of cisterns, of open-like spaces, which in most cases, especially in the granular kind, their outer layers, the outer lamina of the cistern, is lined with ribosomes. And these, of course, are the sites for synthesis of protein from RNA. And the reason that we saw these Nissl bodies in the first place was because of the heavy incrustation with ribosomes rich in RNA, and this, of course, was easily stained by the basic aniline dye that we told you about a minute ago. These other stains here are versions of a family of stains we just mentioned in passing and not mentioned again, so-called reduced silver stains, which were also important in the history of neuro, but are now essentially very little used. And finally, what is this curious picture here? You can see a cell body, because you can see very vaguely the nucleus and the nucleolus, a couple more cell bodies. You see all of these little black spots and fragments? This is one of many modified reduced silver stains which are specific for degenerating axons. About 1952 or 53, a new family of, a subfamily of stains were developed, the so-called Nauta stains, N-A-U-T-A, again named after a man, a very fine histologist, who found that by playing a few games with the tissue, if you made a lesion and then sacrificed your animal 3 or 4 days later, the result of that lesion, of course, produced degeneration out to the terminals. The terminals degenerated, and with some version of a Nauta stain, those degenerating terminals specifically turned black. And so for one of the first times, we had a mode of tracing a connection from A to B, right out to the presynaptic terminals. They had been cruder ways in the past, and we actually learned a great deal of CNS connections from these cruder techniques. Just to give you an idea of the step-by-step progression by which we learn the kinds of things that we're taking for granted today, and you and I are going to be sharing. So I just want to bring that to your attention. Now, again, a drawing from Cajal, because again they are they're historic and they're very beautiful. The dendritic spine. All of you, I'm sure, have heard of spines. They are highly labile structures. The spine selectively, although it's not the only structure that does this, the spine selectively receives presynaptic terminals from other places. In other words, it is a receptacle for presynaptic input coming to this dendrite. Does that mean that the dendritic surface itself receives no input? Not necessarily. As a matter of fact, as you get closer to the soma, to the cell body, more and more presynaptic terminals will also be found on the bare shaft. But in a general way, and this is a fairly safe generalization, the terminals that end up on the spines tend to be facilitatory. And the terminals that end up directly on the shaft or on the surface of the cell body itself, they tend to be inhibitory. So this is a nice dichotomy. There is another thing that I just love about the dendritic spine, and that is that it is not a hard-wired, it is a soft-wired connection. What do I mean by that? When a dendritic system is exposed to a new pattern of input, one of the ways that it responds is by putting out new spines to receive more of this exotic input. And data were generated actually 20, 25 years ago to show that a dendrite is able to begin to push out a fresh dendritic spine within 30 seconds of the arrival of the new input. Isn't that remarkable how labile that is, how plastic that is? Today, with exciting two-photon techniques and the fluorescence that we can engender in cell dendrite systems, we can watch these phenomena over days through little windows in suitably prepared animal structures. Being done here in a number of laboratories, very exciting. We can actually watch the central nervous system respond to the accession of new inputs or to deprivation of a certain family of inputs which it got used to having. Because these spines disappear too. So they can come and they go. So this is the vital, soft-wired part of the nervous system. Whereas the connections to the dendritic shaft and the cell body tend to be hardwired. And once they're made, they persist. And of course, there are all kinds of interesting implications to this kind of fact. Now here we compare our three ways of looking at the nervous system. Here, of course, rather lousy photograph, we see a Golgi-stained cell body, axon, the little initial segment of the axon is right there, and some dendrites. Here, at a very much larger magnification, we see just the cell body, just filled to brimming with missile substance, the endoplasmic reticulum, and the nucleus and the nucleolus. And here, we see this area here, very much magnified in transmission electron microscopy. You know, the electron microscope first became a reality in the, actually the early 40s, and then of course was very much retarded by the Second World War. Then in the 50s, it began to be applied to biological systems, and of course, in our case, to the nervous system. And it's remarkable how it just opened up a whole new world for all of us. what do you see here? Well, all these little spattered dark structures, the little ones, they're ribosomes. These little structures that are essentially RNA-based and which are sites for synthesis of proteins, for instance. And they line, although we don't see them as clearly, they line those endoplasmic reticular cisterns, which somehow are the base of the structures we're talking about. And there are free ribosomes that are also present throughout the cytoplasm, also little sites of synthesis. In addition, we see fragments of mitochondria, and then we see the membrane of the cell narrowing down here and becoming the axon. The axon can be loaded with mitochondria, but interestingly enough, ribosomes and ribosome-related structures, in other words, synthesis, stops at the axon hillock. You can see the membrane of the axon here, and of course, all of this structure outside of the neuron, made up of dendritic branches and axons and some glia and everything else, all of that we sequester under a certain term. Some of you have heard of it, some of you haven't. The term is neuropile, N-E-U-R-O-P-I-L. Neuropile is the combination of all those structures and connections that are just outside the cell. In other words, neuropile makes up, from the point of view of this neuron, the extra neuronal environment. So the word neuropile is one you'll use over and over and over again. I've suggested to you. Now, what are some of the endocellular structures that characterize a neuron? We've already mentioned the endoplasmic reticulum. And there is both rough and smooth varieties. The rough variety is the endoplasmic reticulum studded with these ribosomes. The smooth does not seem to have a ribosomal periphery. And its role apparently is not, therefore, one of protein synthesis. It has other roles, some of which have to do with calcium ion buffering or manipulation. It's a little less clear. But then the cell body, as we say, is absolutely riven. It's just like being in land that is shot through with sandstone caves. The caves are everywhere. That's the endoplasmic reticulum. Another kind of structure, which is also cisternal in nature, and which many people feel is a derivative of smooth endoplasmic reticulum, this other kind of structure, we call Golgi bodies. There's that man's name again. He was everywhere, wasn't he? And the Golgi bodies, again, are three-dimensional caves or cisterns within the cytoplasm. Their role seems to be to complete what the protein synthesizes in the endoplasmic reticulum finished. The Golgi body seems to package the products that are formed by the endoplasmic reticulum. And one of the components of packaging is adding glucose, called glycosylation. So the Golgi body works in a way, in a sense, hand in fist with the endoplasmic reticulum. One manufactures, the other one packages the important molecular components, vesicles, hunks of membrane that will be transported around and inserted, and so forth. So here then are two very important families of endocellular structures. Many of you know that there are things called lysosomes, L-Y-S-O, lyso meaning to cut or to dissolve. Lysosomes within the cytoplasm. And the lysosomes are little bags of chemical which, if released, specifically break down or destroy certain components of the cytoplasm. So the lysosome is a little, it's a little bomb, you might say, so that the cell can keep itself from getting too old. It destroys parts of itself from time to time, and of course replaces them. So the lysosome is an important part of the endocellular aggregate, as are pigment granules, whose roles we usually don't understand. Now, a very dramatic part of the endocellular apparatus, endo of course meaning within, inside, very important part of the endocellular apparatus are the skeletal components. Each cell actually has a skeleton, and if we look carefully, we can vaguely see linear structures in here. See them down there? And I want to spend a little time talking about these linear structures because they have so many fascinating functions. Let's just list what we know. There are three major endocellular skeletal components. The first one, again many of you know this, are microtubules. Microtubules. In size, they're about 25 nanometers in diameter. They're rather interesting. They are made up of, if we make a cross-section through them, we see 13 rod-like protein structures and a central core. They're composed of a polymerizing protein. That is, a protein that can aggregate on itself and grow longer and longer. A polymerizing protein called tubulin. And this system of microtubules are constantly being assembled and disassembled. So it's a very vital, living, breathing rod system. In part, it helps maintain the form of the neuron. But even more exciting, it serves as, I always think of it as sort of the light rail transport within the neuron. Because along the surface of the microtubules occurs a phenomenon that many of you have heard of. The phenomenon is known as axonal transport. Now there are several ways in which communication of information occurs within a neuron axon or a dendritic neuron axon continuum. One of the ways is along the surface membrane, the action potential, which carries information very quickly, right? At least from the soma, out the axon to the periphery. That's the usual direction, although it doesn't have to be that way, but that's the usual direction of the occurs. That was a very fast mode of transport of information. A second, somewhat slower mode for the transport not only of information, but of substance, of material, is this phenomenon that we call axonal transport. Phenomenologically, it was first suspected. Well, I'll tell you how it was first suspected. As a matter of fact, it was first noted by an old medical school sort of friend of mine, who before he came to medical school was working with an investigator, and they did a very simple-minded thing. You know what they did? They got a guinea pig or a rat, I forget which, and they isolated the sciatic nerve, and then they, can you see over this thing? You can't very well, can you? No, bad line of sight. They tied a ligature around that, and they tightened it. And very quickly, on the central nervous system side of the ligature, because now it was narrowed down this way, this began to belly up like that. And they said, not in so many words, but, my gosh, there must be something flowing down that's being dammed up by the ligature. And then, even less intuitively, shortly after that, they found that the area beyond the ligature began to belly out a little bit too. And they said, my gosh, again, there must be something moving back this way that's also being bound, being dammed up by the ligature. They had discovered that there was transport of material along axons, or in this case, along a mass of axons, which is what is a peripheral nerve. And then this was found, of course, in other places. And what we now know is that axonal transport is a ubiquitous phenomenon in all axons, and in dendrites too. There, of course, it would be dendritic transport. So molecules, vesicles, protein, can be carried from the point of synthesis, which is usually in the cell body, out into the dendrites, out along the axon as far as the periphery. In general, there are two kinds of axonal transport, fast and slow. That's not surprising, is it? Fast transport is remarkably fast, up to 300 millimeters a day. That's 30 centimeters. That's about, 16, 17 inches a day. In other words, fast axonal transport, the good-sized axon, is capable of going from my spinal cord out most of the way to the elbow in a day. That's very fast within the nervous system. So that's fast transport. Slow transport, obviously slower, and averages around 1 or 2 millimeters a day, very much more slowly. If the transport is going from the cell body of origin out, away from the cell body, we call that orthograde transport. And if it is pig-headed and it's going the wrong direction, it's going back toward the cell body, we call that retrograde transport. Why on earth would there be retrograde transport? As a matter of fact, it's a very important function, because here's a cell, here's its axon, and here's its terminal. The milieu, the setting in which its terminal terminates, may change with time. And that may make it appropriate for the cell body of origin to change in other appropriate ways to match the new situation here. And that's why molecules coming back and bringing the information are very important. In general, retrograde transport tends to be slow transport. And orthograde transport is more likely to be fast or rapid transport. How does the transport occur? Are there trolleys? I mentioned a light rail line. Oddly enough, there are. This was argued about for a long time, but with very high resolution electron microscopy, I'll show you one in just a moment, it became pretty clear that there are some complex ATPases, which are essentially little molecular systems that seem to run along the surface of the microtubule and carry the molecule on its back. The system that mediates orthograde transport we call the kinesin system. Kinesin. And the system that supports the retrograde type of transport is now called the dynein system. As I say, these apparently are just good, powerful ATPases which carry on their back almost the molecular masses that are moving along the microtubule. Very, very dramatic system. And it certainly emphasizes how alive and pulsing every cell axon apparently is. All right, now these are the microtubules. The next important endocellular skeletal component, I'm watching the clock. I know that there's a limit to your tolerance. The next one is the neurofilament. Approximately 10 nanometers in diameter, made up, they say, of cytokeratins. I've never worked with them, but they are, the neurofilaments are probably the most numerous of endocellular skeletal components. And they also are very important in maintaining the structure and the shape of the axon, of the dendrites, and even of the cell body. The third component is the, usually called the microfilament, about 5 nanometers in diameter, made up of actin, which, by the way, is quite mobile and almost like a rubber band, can stretch or contract. And I find the microfilaments are very exciting because one of the presumed roles of the microfilament is the following. Let's just move this over here for a minute. Here is the membrane of this axon. Here's the membrane of this axon. And then floating in it, all kinds of structures, right? Receptors, channels, and so forth. The microfilaments are supposed to be involved in controlling the placement and the movement of these proteinaceous structures that float in the in the membrane. So they're like the strings that control the puppets. And I find this very, very interesting. This is one of the dynamic roles of these microfilaments. So I wanted you to at least have some idea of those structures. Let's see, is it time for a break yet? Anything else we should do? Let me show you just a few slides and then we'll take a break. I know you're getting a little tired. Let's first as you also know, a significant number, although certainly not all, axons in the nervous system, both central and peripheral, are sheathed with wrappings of a lipoprotein called myelin. Somebody once called the myelin sheath a mammalian invention. Certainly invertebrates, when they want to achieve rapidity of conduction, the only way they can do that is to increase the diameter of the axon. And the giant squid axons are great examples of rapidly conducting axons. Again, myelin hadn't been invented then, and so these axons conduct by virtue of having a larger cross-section, and therefore more surface membrane. If we needed the relatively large number of 50 to 100 meter per second axon types that we indeed have, and we had to rely simply on diameter, we would have heads again that would be difficult getting through doors. But the myelin sheath, as you know, through what we call jumping conduction, saltatory conduction, allows much more rapid conduction to occur on the smaller size. Now, here you see a typical myelin sheath surrounding the axon. And again, as most of you know, there are periodic interruptions in that myelin sheath. They're known as nodes of Ranvier, and this is a very brief, about a 1 micra stop or cessation in the sheath. In general, sodium and potassium ions cannot, and calcium ions, cannot penetrate the sheath. It's a fine insulating membrane. So of course, the emitters and the receptors are located at each of these bare areas, and the action potential can literally jump from one node of Ranvier over the intervening distance. And by the way, that intervening distance is known as an internode, the distance from one node to the other. It jumps across the internode to the next node of Ranvier. And therefore we get this jumping or saltatory conduction. If you're home at Thanksgiving, you feel happy, and you want to be jumping around in the yard or in the apartment, that's known as saltation. And if your parents want to know what in God's name you're doing, tell them it is saltation because of your exaltation. They'll think you've learned a great deal. Here is a cross-section through a tract in the nervous system, and I show it to you because you can clearly see right here a typical node of Ranvier. And if we look carefully, I'm sure we'll see a few more. There's one right here. So these are characteristic of myelinated neurofibers. A word or two about how myelin is laid down, and this is a take-home message. Unfortunately, the top one is sort of lost. What happens is the cell that's going to produce the myelin, in the central nervous system, it's an oligodendrocyte, we'll talk about those. And in the peripheral nervous system, it's a Schwann cell. They're on your sheet. What they do is they wind their cytoplasm around the axon and then progressively wind from outside in. Look at this. See that? So they progressively lay down layers of their cytoplasm, and then lipid is deposited in that. But from outside in, and that's true, as I say, both peripherally and centrally. So here we have two sequences. Remember, when we talked about the development of the cerebral cortex, development is inside out, remember? When you think about the development of the myelin sheath, it is a progressive development from outside in. And that's very useful to remember. Finally, just to show you, here's a hard-working oligodendrocyte. One bridge of cytoplasm here, one bridge here, and one bridge here. This fellow is supporting a number of internodal lengths of myelin on 3 or 4 or 5 adjacent axons. They used to say that Napoleon Bonaparte was able to ride horseback, dictate letters, plan his battle engagements, and make love all at the same time. So the oligodendrocyte is a little bit like Napoleon. Look at all of the axons that it's supporting here. There is a downside to this too, of course, because if you are an individual who is, let's say, developing multiple sclerosis, and somehow, maybe through autoantibodies, you begin to chew up your own oligos, you lose a single oligo. Notice that you'll damage 3 or 5 or more adjacent axons. The Schwann cell, which is like an oligo, but in the peripheral nervous system. Remember, the Schwann cells come from the... What are the Schwann cells derived from embryologically? Anybody remember? Neural crest, yes, that's right. The Schwann cell only supports, we think, one segment of one axon. So no Napoleonic nonsense there, but much more serious. And finally, I wanted to show you this cover from Science magazine a few years ago, a beautiful electron microphotograph, cross-section through an axon. Here in cross-section, by the way, you see the microtubules, and you see the neurofilaments, and probably, I don't know if I can see micros or not. But look at this beautiful multi-laminate myelin sheath. The black portion, of course, is the lipid portion, and the lighter portions are the fragments of the original cytoplasm of the glial cell that generated this. And finally, this just to show you at very high power, it is supposed to be 176,000. I have some questions about it, but these are perhaps part of the microtubule plexus within an axon, with all the little spikes and spines, remember many of which are going to go laterally and control the little protein structures floating in the membrane. And I think this is the last one of this group. I told you about kinesin and dynein. Here's the organelle. Here's the little clump of membrane-bound, membrane-surrounded protein already synthesized. And these little fellows are the kinesin molecules. Notice how they work together to shove this along. It's, and you know, you get some feeling of that maybe from here. I sort of take this on advisement. It's almost too good to be true. But nature sort of surprises. Question in back? No question, okay. By the way, you haven't asked any questions this year yet. And by all means, ask during lectures so we don't want you to forget. So what I'm going to do now is suggest, it's 10 o'clock, take no more than a 10-minute break, because I do want to talk to you about one of my favorite cell types, neuroglia.